China just did something the entire semiconductor industry insisted couldn't happen. Not this decade. Not without the most advanced lithography machines on Earth. And definitely not from a company that's been completely locked out of buying those machines for years. And yet, here we are. Huawei, the Chinese tech giant the United States spent years trying to freeze out of the global chip supply chain, just unveiled a new way to build processors. If the numbers they're presenting hold up, they're talking about matching performance levels associated with 2-nanometer chips, without the one machine that makes 2-nanometer manufacturing possible in the first place. No EUV lithography, no ASML, none of the tools the rest of the chip industry depends on to stay competitive. It sounds impossible. In a lot of ways, it kind of is. But here's what makes this genuinely worth understanding. The idea behind it has nothing to do with making transistors smaller. It's about doing something almost nobody in mainstream chip making has seriously attempted at this scale before. And once you see what it actually is, you'll understand exactly why engineers around the world are watching this closely. For roughly 60 years, the entire technology industry ran on one simple idea. Make things smaller, and everything else gets better. Smaller transistors mean faster chips mean better computers, and better computers mean better everything, downstream of that. This idea had a name, Moore's Law, and it worked so consistently for so long that the industry basically assumed it would just keep going forever. Roughly every 2 years, engineers figured out how to shrink transistors again, packing twice as many onto the same sliver of silicon, and performance would jump while cost dropped. It's genuinely one of the most remarkable sustained streaks in engineering history. We went from thousands of transistors on a single chip in the 1970s to billions by the 2000s to hundreds of billions today. The processor inside a modern smartphone now carries more raw computing power than supercomputers that used to fill entire rooms just decades ago. But here's the part that doesn't make it onto the marketing slides. That streak has been slowing down for years now. The gains keep shrinking. Jumps that used to happen every 2 years now stretch out to 3 or 4. And the cost of staying on that curve has become almost absurd. Building a single leading-edge chip factory today runs somewhere around $20 billion. Developing just one new generation of transistor design can cost $1 billion in research alone before a single working chip ever rolls off the line. TSMC, the Taiwanese company that manufactures chips for Apple, Nvidia, and most of the rest of the industry, is currently fighting for something like a 6% area improvement in its next generation. 6%. That number used to be double digits, often 50% or more between generations. The easy gains are gone, and the remaining ones keep getting harder to squeeze out. For Huawei specifically, though, the challenge isn't just that progress across the whole industry has slowed down. Their problem is far more specific, and it traces directly back to a decision made in Washington. Starting in 2019 and tightening steadily through 2020, the US government imposed sweeping restrictions on which technologies American and allied companies could sell to Huawei. Those restrictions kept getting stricter, and by 2022, Huawei was effectively cut off from the most advanced chip-making equipment in the entire world. The single most important piece of that equipment is a machine called an extreme ultraviolet lithography system, built by a Dutch company called ASML. There's essentially nothing else like it anywhere on the planet. TE machine works by firing a laser at tiny droplets of molten tin with enough energy to briefly turn them into plasma, producing extreme ultraviolet light. That light bounces through a series of mirrors, polished so precisely that a single stray atom of contamination could ruin them before being used to print circuit patterns onto silicon too small to see under an ordinary microscope. Each machine costs roughly $200 million, weighs about as much as 2 commercial airliners, and is the reason companies like TSMC and Samsung can currently manufacture chips at the 3-nanometer and 2-nanometer level. Huawei can't buy one. And SMICE, the Chinese chipmaker that manufactures Huawei's processors, can't buy one either. So what do you actually do when you're cut off from the single most important tool in your entire industry? You get creative. SMIC has already done something genuinely impressive using older technology, relying on deep ultraviolet lithography systems that use a considerably less powerful type of light to print circuit patterns. That older technology was never originally designed to produce chips this small. To work around that limitation, they use a technique called multi-patterning, breaking one extremely fine pattern into several simpler steps, each printed separately and then carefully layered together afterward, similar to drawing a detailed image by laying down one color at a time across multiple passes. Through sheer engineering persistence, SMIC pushed this older approach considerably further than most outside experts thought possible, reaching what's roughly considered a 7-nanometer equivalent process. That's genuinely impressive on its own, but every additional step adds cost, complexity, and another opportunity for something to go wrong, and there's a hard ceiling on how far this approach can realistically be pushed. Huawei's engineers clearly saw that ceiling coming, so instead of continuing that same losing battle, they started asking a fundamentally different question. What if shrinking transistors isn't actually the only path left toward making chips better? Here's the part that genuinely surprised a lot of people once they dug into it. Modern computer chips aren't mostly limited anymore by how fast their individual transistors can physically switch on and off. They're increasingly limited by something else entirely. How long it takes information to travel from one part of the chip to another. Sit with that for a second. The actual thinking part of a chip isn't really the bottleneck anymore. The moving information around part is. According to Huawei's own presentation, more than 80% of the energy consumed inside a modern computing system can go toward simply moving data from place to place, not toward actually performing calculations at all. 80%? That's not an exaggeration or a typo. The chip is spending the overwhelming majority of its energy budget playing messenger, not doing math. To understand why that happens, it helps to picture what a chip actually looks like on the inside. Imagine an incredibly dense miniature city packed with hundreds of billions of tiny workers, all crammed into an area smaller than your fingernail. Those workers are the transistors, actually performing the computation. But they're connected by a sprawling network of tiny metal wires stretched across more than 20 separate layers stacked inside the chip. Every time information travels through one of those wires, two physical effects slow it down. First, the wire resists the flow of electrical signal, not unlike how a narrow pipe slows down water. Second, the wire behaves a little like a tiny battery that has to charge up and drain every single time a signal passes through it. Engineers call this combined effect RC delay, and the longer the wire, the worse both effects become. This is the main reason clock speeds in consumer processors have barely budged in roughly 15 years. We're not fundamentally limited by how fast transistors can switch anymore. We're limited by how fast signals can physically travel between them. So here's the insight that changes the entire equation. If the core problem is distance, what if you could simply make the distances shorter, not by shrinking the transistors themselves, but by rearranging where they physically sit relative to each other? What if, instead of spreading a chip out flat like a city built across a single plane, you stacked sections of it vertically on top of each other, more like a skyscraper? That's the core idea behind what Huawei just announced. They're calling it tau scaling, and the name reflects the fact that they're specifically optimizing for time, meaning the time it takes for signals to physically travel across the chip. The underlying concept is actually easy to picture. Take a piece of paper covered edge to edge in text. The words in the top left corner sit far away from the words in the bottom right corner. Now fold that papa. Centimeters apart are suddenly sitting right next to each other, separated only by the thickness of the paper itself. That's essentially what Huawei wants to do with an actual chip. Take a processor that would normally be laid out flat, split the logic circuitry into sections, and fold one half directly on top of the other. Signals that used to have to travel several millimeters across flat silicon now only need to travel a tiny fraction of that distance vertically instead. Millimeters shrink down to microns. The total journey shrinks by roughly a factor of 1,000, and when that journey shrinks, so does the delay, the energy consumption, and the heat generated by all that constant data movement. In their early results, Huawei reported achieving a transistor density of 238 million transistors per square millimeter using this folded, stacked approach, roughly 55% more logic packed into the same physical footprint compared to their existing flat chip design. And on a roadmap stretching out to around 2031, they're claiming this general approach could eventually deliver performance comparable to what you'd expect from a 1.4 nanometer chip, entirely without ever needing extreme ultraviolet lithography at all. Before getting too excited about that particular number, though, there's something important to understand, and it's a detail a lot of the initial headlines covering the story got wrong. When chip companies talk about nanometer figures today, those numbers function more as a marketing label than as an actual physical measurement. A 2 nanometer chip doesn't mean the transistors inside it are literally 2 nanometers wide. The number has become industry shorthand for a general level of performance and transistor density. What Huawei is actually claiming isn't that they've invented some entirely new type of transistor, measuring 1.4 nanometers across. They're claiming that by stacking 2 layers of their existing, already mature chip designs on top of each other, they can pack enough total transistors into a given area to compete with whatever a chip labeled 1.4 nanometer would be capable of delivering. That's still a genuinely impressive claim, but it's a fundamentally different kind of impressive. Stacking 2 mature manufacturing processes together doesn't create some brand new manufacturing process from scratch. It's closer to a clever system-level engineering trick than a true transistor-level breakthrough. The real breakthrough, assuming they can actually deliver on it, lies somewhere else entirely. When Huawei presented this plan, one specific number caught the attention of pretty much every semiconductor engineer who saw it, and it wasn't the 1.4 nanometer figure. It was a different number entirely, 1.5 microns. That's the bonding pitch Huawei is targeting for connecting their stacked chip layers together. Here's why that particular number matters so much. When you stack two chip layers directly on top of each other, those two layers need to communicate constantly, billions of times every single second. The physical connections between them are extremely tiny copper dots that bond directly from one layer straight through to the other. The smaller those dots are and the closer together you can pack them, the more total connections you can fit into a given area, and the faster information can move between the stacked layers. Spacing between these connection points is called the bonding pitch. Today, the best bonding pitch anywhere in the world sits at roughly 9 microns, which is what AMD currently uses in its 3D V-cache memory stacking technology. TSMC and Intel operate in roughly that same general range. Huawei is talking about pushing that figure down to 1.5 microns, 6 times smaller than today's current best, which works out to roughly 6 times more connections packed into the same unit of area. And here's exactly what makes that particular claim so striking to people who actually understand the manufacturing challenge involved. Going from 9 microns down to 1.5 microns isn't a small incremental step forward. It requires genuinely new equipment, new materials, new manufacturing processes, and entirely new methods for verifying whether each individual bond actually worked correctly. It's the kind of leap the broader industry usually takes an entire decade to achieve, working through one small incrementals, improvement at a time. If Huawei genuinely manages to pull this off, it fundamentally changes the underlying math on everything. With enough dense connections running between the stacked layers, the two chips stop behaving like two separate components entirely and start functioning more like one single, unified, extremely dense processor. The seam between them essentially disappears from a pure performance standpoint. That's the full vision here. But then you run straight into a wall, and it's a genuinely hot one. This is the exact point in the story where basic physics shows up and complicates everything. Memory chips run relatively cool. They mostly just sit there quietly, holding data without doing much active work. Logic chips are a completely different story. Logic chips are switching billions of times every single second, and every single switch generates a small amount of waste heat. Multiply that across hundreds of billions of transistors, all running at full speed simultaneously, and you end up with a chip that heats up very quickly. Right now, that heat mostly escapes through the top and bottom surfaces of the chip, flowing into a heat spreader and then into a broader cooling system. Inside a data center, that cooling infrastructure can be enormous. Liquid cooling pipes, giant banks of fans, sometimes entire buildings specifically engineered around efficiently moving heat away from processors. In that kind of environment, a genuinely hot chip is still manageable. Huawei's first practical target for this particular technology, though, isn't a data center chip at all. It's a Kirin processor meant for smartphones. Your phone has no fans, no liquid cooling loop, and essentially no spare room for elaborate cooling hardware. It has a thin slice of metal and, if you're lucky, a small graphite sheet to help spread heat around internally, and it sits directly in your hand, which means it physically can't be allowed to get too hot. When you stack one genuinely hot logic chip directly on top of another hot logic chip, the heat generated by the bottom layer has nowhere convenient to escape to. T-he layer sitting on top traps that heat in place. You've essentially built a tiny thermal sandwich, and the filling is actively on fire. This isn't a minor, easily solvable engineering detail. It's genuinely one of the hardest open problems in this entire corner of the physical world right now. Some research teams elsewhere in the industry are actively exploring materials that conduct heat more efficiently, or microscopic channels etched directly into the silicon itself designed to carry cooling fluid straight through the stacked chip layers. But none of those particular solutions have been proven at real mass production scale just yet. Whether Huawei actually has a credible, working answer to this specific heat problem is really the question that determines whether tau scaling ends up being a genuine, practical roadmap, or simply a very impressive-sounding presentation. If they solve it, the roadmap looks genuinely extraordinary. If they don't, this entire stacked logic approach runs straight into a hard ceiling long before it ever reaches its full potential. That's not a criticism of the idea itself. It's simply an honest description of exactly where things currently stand. So stepping back for a moment, what does tau scaling actually change? Assuming everything genuinely works as planned, Moore's law was historically special because it made chips both better and cheaper at the exact same time. Every new generation delivered more raw performance while simultaneously costing less per individual transistor. That's an almost magical combination, and it's precisely what eventually put a genuine computer into every single pocket on the planet. Tau scaling doesn't offer that same combination. Stacking chips together is inherently more expensive than not stacking them. It requires considerably more precise manufacturing, more total processing steps, and more extensive testing at every stage. The bonding process required at 1.5 microns is simply going to cost more than the bonding process currently used at 9 microns. So what you're really trading here is cost in exchange for performance. You gain more raw capability packed into the same physical footprint, but you pay a real price for that gain. That's still genuinely valuable, especially in a world where traditional transistor scaling has slowed to a crawl, but it represents a fundamentally different kind of progress than what powered the industry for the better part of 6 decades. It's also worth noting that Huawei isn't the only company thinking along these particular lines. AMD already stacks memory directly on top of logic in some of its current processors. High bandwidth memory technology already stacks a dozen or more memory dies directly on top of each other. Intel and TSMC both maintain their own three-dimensional chip packaging roadmaps as well. And deep inside research labs scattered around the world, engineers are actively working on transistors designed to stack vertically at the atomic level. The broader industry was already heading in this general direction before Huawei's announcement. What Huawei is doing is pushing that same underlying idea considerably harder and faster than anyone else currently attempting it, partly out of sheer necessity given their restricted access to advanced lithography, and partly because they clearly have the engineering talent available to genuinely attempt it. That 1.5 micron bonding pitch, if they actually manage to achieve it in practice, would represent a genuine world. First, the heat problem is real, but it isn't necessarily impossible to eventually solve, and the density numbers they're already demonstrating from early AMPL imitations don't appear to be fabricated. They're simply a different kind of achievement than possessing an actual, true 1.4 nanometer manufacturing process. It's something else entirely, arguably a category that doesn't yet have a clean, widely agreed upon name. Maybe the most honest way to put it is this. Huawei found a door in a wall that most of the rest of the industry had simply assumed was solid. Whether that particular door actually leads where they currently think it does is something we'll only find out over the next several years. Huawei's own roadmap places the full realization of tau scaling at around 2031, roughly 5 years from now, and a great deal can still change across the semiconductor industry in that span of time. In the nearer term, the thing worth watching closely is whether SMICs can actually manufacture these bonded chips at real production scale with acceptable yields, meaning the percentage of manufactured chips that actually function correctly. In advanced chip manufacturing, getting yield right is frequently harder than getting the underlying design right in the first place. A chip that performs beautifully inside a research lab but fails 60% of the time on an actual production line isn't a viable product yet. The thermal story is the other major thread worth tracking closely, as more concrete details emerge about exactly how Huawei plans to manage heat. Inside a fully stacked Kirin smartphone chip, that will be the clearest available signal of whether this represents genuinely production-ready engineering or still largely an aspirational roadmap. And then there's the broader question of what this means for the rest of the global chip industry. If this approach genuinely works, and 1.5 micron bonding becomes a real manufacturable technology, other major companies will want access to it too. TSMC and Intel will almost certainly accelerate their own three-dimensional packaging programs in response. The overall race won't simply be over, it'll just shift into an entirely new arena. That's honestly the beautiful and occasionally maddening thing about semiconductor engineering as a field. Every time someone declares something impossible, someone else eventually goes and builds a version of it anyway. Not always in exactly the way the skeptics originally imagined, and not always on the timeline that gets promised, but eventually, more often than not, it happens. Huawei's announcement isn't proof that they've already won this particular race. It's proof that they're genuinely still playing. And in a competition this consequential, simply remaining a serious player counts for quite a lot.